We've been talking about an AR1 process. Why is there a 1 in AR1? Well, it doesn't have to be limited to 1. An AR1 process, a given data value depends only on the single previous value. It could depend on more than just 1. Suppose that instead of x depending only on the previous value, it depended on the 2 previous values. An analogous equation would be this, where a given value is some constant times the previous value plus some different constant times the previous 2 times value plus a white noise value. This gives what is known as an AR2 process that generates AR2 noise. We can write it using the lag operator just as we did with an AR1 process. That looks like this, a particular constant times the lag operator plus a different constant times the lag operator squared, which is the lag 2 times operator. And we can arrange things algebraically to say that it's this operator times the data gives white noise, and we can even give a name to that operator. We can call it uppercase Greek letter phi, the AR2 operator. Well, previously, we benefited from being able to invert the AR1 operator. Can we invert the AR2 operator? Well, to investigate that, let's define something called the characteristic polynomial. We'll just take the operator, only instead of applying it as coefficients times powers of the lag operator, let's make it coefficients times powers of some number. I'll allow it to be a complex number. We'll call it z. Well, we can find the roots of that complex, of this polynomial. Call them z1 and z2, and we can write the characteristic polynomial in this form. Well, if we can write the characteristic polynomial in that form, then we can write the AR operator in this form. This can be inverted if both of its factors can be inverted. They can both be inverted if both of the absolute values of the roots of the characteristic polynomial are greater than 1. If they're greater than 1, then 1 divided by them is less than 1, which makes each term individually invertible. When that happens, we say that the AR2 process is causal. Why stop at 2? We can define an ARP process, an order P autoregressive process, as a given value is some constant times the previous value, plus some different constant times the 2 times previous value, etc., 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 all the way up to some other constant times the P previous value data. And at the end, we'll tack on white noise so as to make the whole thing stochastic or random. Once again, we can write this in terms of the lag operator and use it to define an autoregressive operator of any order P that we want. And the defining property is that that autoregressive operator, when operating on the data, gives us a white noise process. If the roots of the characteristic polynomial all have the property that their absolute values are greater than 1, then our operator is invertible, and that means that the process is causal. Inverting it puts it in this form, where the data values are the inverse operator operating on a white noise series. I'll call that inverse operator psi, the uppercase Greek letter psi, and it will correspond to a bunch of coefficients psi sub n, which are the coefficients of the powers of the lag operator in its operator expansion. And that means that the data values are this infinite sum of psi coefficients times white noise values. By the way, in all cases, the 0 component, psi sub 0, will be equal to 1. This defines the operator psi and its associated coefficients, and it also enables us to compute the autocovariance function for some lag, let's say, which is greater than or equal to 0. The autocovariance function is the expected value of the product of lagged data values, and that's equal to the variance of the white noise times this sum of psi values times lagged psi values. There's another way to get the autocovariance function. Let's take the defining equation, which looks like this. Then let's just directly compute the expected value of data with lagged data values. We can expand it algebraically to get this expression. And when the lag is greater than 0, that turns out to be this. The autocovariance at lag h is the sum of the constants times the autocovariances at lags different from h, in fact, smaller than h. It's very similar to our actual autoregressive process equation, except we're not adding white noise on the end because the autocovariances aren't random variables, they're just properties of the AR process. An example of applying this is to, let's say, take an AR2 process. We could say that the autocovariance at lag 1 is phi1 times the autocovariance at lag 0 plus phi2 times the autocovariance at lag negative 1. Now, the autocovariance at lag negative 1 is the same as the autocovariance at lag 1, so I can substitute that to get this form. And then I can manipulate this algebraically quite easily to say that the lag 1 autocovariance is this expression times the lag 0 autocovariance. That means that the lag 1 autocorrelation is this expression. So just by using this simple trick, we were able to compute the lag 1 autocorrelation. For lags greater than 1, we can use our basic equation to compute further values recursively. So we can compute all of them that we want to by using the recursive formula to go further and further. I'm going to end this particular section by talking about a special case. Let's consider an AR1 process when the AR1 coefficient is equal to 1. In that case, a given data value is equal to the previous data value plus a white noise term. As we carry further and further, we'll keep adding more and more white noise terms. We can put it another way by using the lag operator, but notice that the coefficient phi, which would ordinarily be there, is equal to 1, so I haven't even bothered to write it. And I can also write it in this form as in 1 minus the lag operator, operating on the data series, gives a white noise process. In this case, with this process, the x values are the cumulative sums of white noise. Another name for this is a random walk. This process is very interesting, has a lot of applications. We'll talk a good deal about it more in later lessons, but for now I'm just going to mention it. By the way, the important thing to realize is that this process is not stationary. In particular, let's suppose that the first value is equal to 0. The next value would be that plus a white noise term. The next value after that would be plus another white noise term. It would be the cumulative sums of white noise terms. And one thing we can discover, if you want to analyze it, might be worthwhile and interesting to do so, is that the variance of the data values is not constant. It increases as the values go further forward in time. In fact, for this particular process, the variance of the jth data value will be j times the variance of the white noise process. I will note, by the way, that 1 minus the lag operator is also called the first difference operator. We spoke of it some time ago. And for this kind of random walk, the first difference of the time series is a white noise series, but the time series itself is not stationary.